Gotch, I may say, if I begin on Tuesday, then on Friday evening, say between 7 and 8, I may say, look, if you can, join me because I will be doing the Gotch topic that we have covered. I'll be doing it on R. I will use my commands on R because from my experience, when we get into chapter 4, the author of our textbook, he uses his own program. So he doesn't go out there and bring packages. So that's certainly good because I think his program is good enough. So I can run his programs and use his commands, but then I want to go out there and get packages I have used before that I know are easier for you to handle, especially after this class, okay? After this class. Okay, so after this class, if you want to continue with R and training yourself with R and working with R, then you can use packages that I will introduce you to that will handle Gotch, okay? But then the one developed by the author of the textbook is also good. It's also simple, but it's his. And if tomorrow he doesn't give, if he changes it and doesn't give us access, then you cannot use that. So when we begin Gotch, during that week, I'll set aside time, probably for me, given my teaching schedule and all the administrative things I do, will be on Friday from 7, maybe 7 to 8. I will do it. If nobody comes, that's okay. I will just do it, test it all out, run it. Of course, I'll record everything. I'll give you the command. I'll annotate the command. And then if you have time over the weekend, you can run it yourself. And then if you have questions, you can ask me. But anybody who can come at that time can come, because I don't believe if I say 7 to 8 on Friday, I don't believe all of you can come. But if you cannot come, that's okay, because everything I do, I will record, post it, so you can watch it and then ask me questions in class later, okay? Or outside of class. So that's the way I plan to do it when we get to Gotch. But so far in chapter 2 and chapter 1, the commands in the textbook are general enough because they use zoo, they use XTS, and they use all those packages that they told, FBasic, all those packages they told us on page 12. So those are general, publicly available packages. But whenever he uses his own package that he wrote, then I will do an hour session myself using publicly available packages, okay? So that's the way I want to handle it roughly when we get into Gotch. All right, did somebody make what was the highest? The information is hidden, but the general distribution is given. It says on the bottom, highest score is okay. Yeah, okay, you guys can figure that out. But ask me other questions. All right, any questions about what I said? So who was that asked me about final? Danny, was that you? Was it Danny that asked me about the final?
Yeah, it was.
Okay. Okay, so for now, unless all of you tell me otherwise, for now, I'm thinking the final exam will be multiple choice. Probably the same format as the midterm exam, but again, we can discuss that as we move forward. But again, I would never ask you to do an hour session for my exam. I wouldn't do that. I may just ask you, give you an hour result and ask you questions based on that, just like I did a couple of times on the midterm exam. One thing, I am not bringing the midterm exam to class like this to discuss, because during registration for this class, I think 49 or 50 students registered, but I didn't see 49 or so students take the exam. And I don't have information for like a couple of them. If a few of them dropped, and I see evidence that they dropped, but a couple of them, I'm not sure. So I don't know what's going on, whether they are sick with COVID or their family, I don't know. So I'm just assuming, and that's why I kind of delayed giving you your midterm results until Friday afternoon. I was planning to give it to you Friday morning because I wasn't sure. All right. So I don't want to bring it to general class and discuss in case maybe one or two people didn't take it and they will tell me they haven't taken it. Then I have to figure out a way to give it to them. But I can see you guys one-on-one, okay? That's something that it will take more of my time, but I think some of you, especially if you consider that you didn't do as well as you wanted, I kind of want to see you one-on-one, so I can figure out what's going on and how we can move forward with you doing much better. I'll be happy if everybody in this class makes an A, obviously, I'll be happier. But it doesn't typically happen that everybody in class makes an A. But I want everybody to do as well as you can do. I mean, if you make a C minus or D in this class, that's not well, but by any stretch of the imagination. But if everybody makes, and the lowest grade is a B in this class, I'm happy. That I'm happier than if the lowest case is an F. You understand? So I want to work with each of you to do as well as you want to do, especially if this midterm exam you haven't done well and you haven't been doing well in the homework. I really want to see you one-on-one, so you and I can figure out how we can move you forward, okay? All right, so I have said my piece, but if you have any questions, you can ask me, and then I'll answer before I begin to record and I'll teach class. I have this week, I have two things to teach this week that I'll begin to teach them today. They are, and it will be totally non-technical. I'm not going to write and use any number. I'll just show you, review with you what you have done with Echo 4000 as a setup to what I want to discuss, okay? So I'll wait for a minute or two and ask you, does anybody have any general questions about where we have come from up till now?
So, just to say, so like the grade on Blackboard was the final grade. There was no like curve added or anything, or that was the final grade for the midterm.
No, the midterm I showed 2 columns, right? Did you guys see 2 columns?
I just saw the one grade on under grades out of 100.
Wait. Can anybody tell me, anybody else in this class, did you see 2 columns of grades? Anybody tell me by voice, because I think
Yes.
Okay.
I mean, there's one curved and then not curved one. So there
yes.
should be 2.
So the one that is not curved, it's who asked me that first one? Joseph?
Yes.
Okay. So if you go to Blackboard under Grade Center, I don't know how students access their grades, but I think it's the same thing. If you go to Blackboard and you go not the top part that says course and all that, course, syllabus and everything. If you go further down, it shows Grade Center, and if you click there, if you go to the general, what do they call them? General Grade Center, you will see 2 columns. I made 2 columns available, and also there's a column I think for homework, right? And if you 2 columns for midterm, one says midterm score, and then the other one says midterm curved. So the midterm score is your raw score. That's what you made coming from the midterm exam. But the second one, midterm curve, is a curved grade, okay?
Really?
All right, so check it. If you still have problems, let me know. And after class, we can figure it out. All right. But I think other people saw 2 columns. All right. Any other issues? Any other questions? Okay. So I want to, so let me begin to record now so that those who couldn't come to class can have access to this.
This meeting is being recorded.
Okay, hi again, everybody. It's very nice to see you. So this is the first class after the midterm exam. And so everything we do from now till the end of the semester will be fair game for the final exam, plus some part of the midterm, because this class is kind of cumulative, okay? Autoregressive is autoregressive is autoregressive, no matter what chapter you are. So the material is cumulative in this class. And so for the final exam, we shall also use materials from the first half. But again, I'll give you all the information you need. But tonight, I want to continue with what we have done. So up until before the midterm exam, I think the last class before the midterm exam, I had come in and I had generated an AR1 a number of AR1 time series with known coefficients. I generated AR1, I generated AR2, I generated AR3, okay, using a random series generator. So you and I were certain that the what we called AR1 was truly AR1, what we called AR2 was truly AR2, and what we called AR3 was truly AR3, because I generated them, I simulated them. And then we looked at the properties of AR. For example, the AR1 model. As 3 of them are AR models, autoregressive models, we know that are you okay, Joseph?
Yeah, sorry.
Okay. We know that for autoregressive models, that if you look at the ACF, again, what is the ACF? If you look at the autocorrelation function, and you see the autocorrelation function smoothly declining, exponentially declining, then that may give you, the first thing I'll think about is, this looks like an AR model with positive coefficient on the lag variable. That is the number attached to xt minus 1. If it's an AR1, that number is positive because it's going from up to down smoothly above the 0 line. But if it's going below and up, below the 0 line, the 0 line is here, but it is smoothly going up like this, then what do we say? It's probably an AR1 model with negative coefficient. Okay, we saw that. All right. But then if we suspect it's an AR model, autoregressive model, is declining like this, how do we know whether it's an AR1 or AR2 or AR3? Does anybody remember? What new concept did I introduce before the midterm exam that says, in addition to the ACF, bingo, this is something else you can use to determine that even though it's an AR model, it could be AR1, AR2, AR3, AR9, AR10, AR12. Which one do we, what do we introduce? Yes, Danny?
A partial autocorrelation function.
Exactly, PACF, thank you, Danny. So we introduced PACF because we said, in addition to the ACF smoothly declining, if you introduce the PACF for any of the autoregressive models, there will be no smooth decline. There will be bam, bam, bam. There will be straight lines. But if it's an AR1 model, all those straight lines would be inside of the confidence interval. Okay? Except one, except the line on lag 1, except the partial autocorrelation number at lag 1. That will go beyond, that will break the ceiling. If it's an AR2, then the ACF will smoothly decline. The PACF will be straight line, straight line, straight line, straight line at each lag. But then only the straight lines at lag 1 and at lag 2 will break through the barrier. Okay? That will give us a hint, that would let us know to a large degree of confidence within our confidence level that it's an AR model, but then it's an AR2 model. So when you want to identify whether it's an AR model, it's very good to look at the ACF. The shape of the ACF will generally tell us if it's an AR model. And next week, I will introduce us to a moving average model, not AR, but MA. And you will see that if you look, the shape of the the shape of the ACF for the MA model is totally different from the shape of the ACF for an autoregressive model. Okay. In fact, let me just, please don't be confused. But I'm sorry. I know my students like Danny, you're kind of salivating now. Say, Professor, give us a hint. I know. All right. But so let me give you a hint. A moving average model if, for example, suppose you have a series and you don't know whether it's AR or an MA model, and you do the ACF, and the ACF is smoothly declining, then you can safely say it's not an MA, it's an AR model because it's smoothly declining. Okay? But if the ACF happens to look like the PACF of an AR model, what does the PACF look like? Just straight lines. Bingo, 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 straight lines. Nothing joined at all, no curve, nothing joined. If it's a straight line, then that's the hint. If the ACF is a straight line, that's the hint, it's an MA model. So for the AR and MA model, it's like their ACFs and PACFs are reversed. You will see that next week. I'm just giving you a preview, okay? All right. So, but let's go back to an autoregressive model now. An autoregressive model, the ACF, the autocorrelation function for an autoregressive model is typically smooth. And the PACF is discrete lines, single lines, single lines, single lines. And if the PACF is a single line breaking through the confidence lines, and all other partial autocorrelation numbers, each line up to maybe 12 lags, each line is within the confidence interval, then that's an AR1 model. So for an AR1 model, the autocorrelation function is smooth. The PACF is discrete, straight lines at each lag, but it's an AR1 if the line at lag 1 breaks through the confidence level, the confidence interval, either up or down. Okay. If it's an AR2 model, then the line for the PACF at lag 1 and the line for the PACF at lag 2 will break through the confidence interval. That's an AR2. Then the PACFs for all other lags would be within the confidence bound. Okay, so that's how we figure it out. Okay, but that's that's using our eyeballs. We look at the graph and say, oh, bingo, we suspect to 95% confidence. If our confidence, up and down lines, if our confidence are 2 standard deviations up, 2 standard deviations below, then that's alpha 5%. That means confidence level is 95%. Then we can say at 95%, with 95% confidence, I can say this series, because its autocorrelation function is like this and its PACF is like this, I can say this series, I am 95% confident that it's an AR2 model. Okay, all right. But I want to introduce us to another, you see, because we're dealing with statistics, econometrics, and we're saying with 95% confidence. What does with 95% confidence mean? That means I am 5% probably not confident. I mean, that's the layman's language, right? So if I say I'm 95% confident that this series, Microsoft series, is an AR2 model because I observe the autocorrelation function and I observe the PACF, partial autocorrelation, I can say with 95% confidence, I can say this Microsoft series, 10 years of monthly data, is an AR2 model. It's an AR2 series, okay? Or that I can use an AR2 model to represent it. If I'm 95% confident, what does that mean? I'm 5% not confident in layman's terms. That means 5 out of 100 times I can go wrong. It might actually not be an AR2 model. So 5%, 5 times out of 100 times, I'll make a mistake. But 95 times out of 100, I'm sure it's an AR2 model. That means 5% I could go wrong. That means 1 time every 20 times I can go wrong. Once in 20 days, 1 day out of 20 days, I can go wrong. That's if if you think 5 days a week, then once a month, 1 day in a month, I can go wrong. I can say, hey, bingo, this is an AR2 model, but 1 day out of 1 month, it's not, and so on. So the bottom line is, in statistics and econometrics, as many tests as we can use to try to find out what kind of series, what kind of model we have, we can become much more confident. Okay? So what I want to discuss tonight, or what I want to discuss with you tonight, in totally non-technical terms, there'll be no R program tonight, nothing. But I want to kind of ask you guys to follow me with your intuition. And if I lose you, just stop me, and I will explain it as many times as possible and continue on Thursday. But it's a really easy concept. I was thinking about it earlier today, and so I said, let me go back to Echo 4000 and try to begin with what you have studied before, and I'm sure you understand it before, and try to use it to make sense with what I'm going to introduce to you today. Before I do that, Alec, you were asking a question that some grades are more than 100%. I'm sure you know why, right? If you check the grade distribution I put on Blackboard. Okay. Yeah, Alec, you know why. So check that.
Okay, thank you.
It's because of the curve.
Got it.
And so if you got 106%,
come upstairs for dinner.
that means you scored more than 100. That means on the final exam, I'm going to add 106 points to your overall grade before I do the averaging. If you got 102, then the extra 2 points beyond 100, I'm going to add it when I do the overall grade average of this class, okay?
Got it.
Okay, so everybody, I think, benefits from the curve. Not if you did well, you benefit. If you didn't do well, you benefit, okay? And move everybody up, okay.
Thank
you. Sure. So I want to explain, I want to begin. So I have, before the class, I went and typed up these 3 equations. I hope you can see the equations 1, 2, 3. So I didn't use the equation editor. So instead of B0 subscript, I put 0 in parentheses. So please forgive me. And then on the right-hand side of each equation, I put something called R squared, okay? In statistics, or at least in Echo 4000, you came across the concept of R squared, yes? Can anybody just tell me? Again, I'm drinking Coca-Cola with you near Baruch, or I'm drinking a glass of wine with you in the cafeteria somewhere downstairs at Baruch. Oh my God. I really cannot wait to go back to school. I can wait, but I cannot wait to see everybody. So can anybody, I'm having coffee with you in the lounge downstairs at the vertical campus. And we're relaxed. It's a Friday, you know, everybody is kind of rushing home. And I just came downstairs to buy coffee, and I saw you, and 5 minutes, 10 minutes, we're just kind of talking. And I say, oh, by the way, can you, we're kind of talking about what you learned in Echo 4000. And you mentioned R squared. And I say, okay, can you explain it to me? What's R squared? Please don't be technical. Just talk to me. I'm having coffee with you downstairs, okay? And we're just shooting the breeze, and we're just relaxed and everything. Don't use any jargon. Can you tell me what R squared means for equation 1? Anybody?
Yes.
Okay, who's speaking?
Alec.
Alec, yes, talk to me.
So,
excuse me, Alec, in this equation 1, R squared is 80%. So try and use the 80%, okay? Sorry.
Okay, so basically, R squared shows how well our prediction through the regression model fits the actual data set. And so in this case, what we are predicting through the regression X1 for the regressor Y fits around 80%. So basically, our estimation of Y is 80% accurate towards what I actually is from the
Okay.
observations.
Okay, that's a very nice try. Excellent. Okay, thank you. I will caution you again. Again, I know because I teach econometrics, I teach statistics, and I made these mistakes when I was growing up in school, just like many of you are. You're just taking this for the first time. Please, everybody, be careful when you run a regression. When we have run a regression, what have we done? We have done, and Alec, you use the correct term, we have done estimation, right? That means we took historical data and then we said we think Y and X have a relationship, yes? But what is that kind of relationship? Then we run a regression. We use historical values of Y, for example, return on IBM, and then we use X, maybe percent return on the S&P 500. So we run Y, historical return, either monthly return or daily return, for whatever. We run for IBM, Y variable, and S&P 500, the X variable, and we run it, and we get the equations. For example, return to IBM Y equals 4.5, that's BO, plus 2.5 times return to S&P 500. So when we do estimation, we are using historical data. Yes, everybody knows this. So just process it. You know it. You've passed those classes. Okay. So that's estimation. That is, we have used the historical data to estimate this, to do OLS for equation 1, and from OLS we get the intercept BO 3.5 and of whatever 3.5, and then we get B1 at 2.5. Okay. Now, if we want to forecast, and Alec, you use those two terms interchangeably, but they should not. Sometimes we use them, we mix them up because we understand. So maybe you understand that they are different, but anybody listening to you may not understand they are different. So when you estimate using by running OLS and historical data, you want to find what is B0 and B1, right? You want to find the numbers. 3.5 plus 2.5 times X1. Now, if you want to forecast, that's different. Then you forecast what you think S&P 500 will gain. Maybe you say over the next 1 year, I forecast that S&P 500 will gain 10%. That's a forecast. So if S&P 500 you forecast will gain 10%, then you take that 10% as X1, you plug it into the equation, multiply that by 2.5, that's B1, the slope, and you add 3.5, the intercept, and you say, bingo, I forecast that IBM will return this number. So when you do OLS and you run regression with historical data, you are estimating that model. You are trying to find B0 and B1 based on past numbers. And then when you say B1 is, in this example, B0 is 3.5 and B1 is 2.5, then you say, okay, that you believe Y equals 3.5 plus 2.5 X1. You believe that equation works very well. Why? Because the R squared is 80%. That is, that equation and the data you used tells you that the changes in X1, if X1 is S&P 500, these changes in S&P 500 return explain 80% of the changes in Y. If Y is a return to IBM, then you are saying using the historical numbers data you use to run the regression, and you get the equation Y equals 3.5 plus 2.5 X1. If R squared is 80%, that tells you that that X1 is useful in explaining X2. That is, changes in X1 explain changes in X2 to the tune of 80%. That's what you try to explain, Alec, right? That's what you mean.
Yes.
Okay, that's what everybody understood from Echo 4000. Fantastic. Okay. All right. Now let us say again. Let us say that y, the dependent variable in equation 1, 2, 3. Let us say y is the sales of Tesla's cars, the cars sold by Tesla. Let us say y tells me how many dollars Tesla got by selling all those electric cars in the past 10 years. Okay, suppose we get 10 years of sales data for Tesla's cars, maybe month by month. And Y represents sales of Tesla's car every month. So we got 10 years of monthly data for sales. That's Y. And then we got 10 years of how much Tesla spends advertising. So X1 is advertising expenditure. So Tesla spent $1 million in January 2018. That's X1. But that same year, that same month, it spent $10 million. It got sales of $50 million of the Tesla's cars. So Y for that month will be 50 million. Okay, so in equation 1, everybody, sales of Tesla car equals a constant plus B1 times advertising expenditure. How much Tesla spent during the month. Okay. Now, and so we are saying advertising expenditure explains 80% of sales. That's the easy way of interpreting it. But the technical way of interpreting it is that changes in advertising expenditure explain 80% of changes in sales of Tesla cars. R squared is 80. Okay, now everybody, please listen carefully. Okay. And this is no trick question because you've taken Echo 4000. Now, suppose I introduce another variable, X2. So in equation 2, I have sales of Tesla cars every month. X1 is still advertising expenditure. But then I introduced to that, so in equation 1, only advertising expenditure. But in equation 2, in addition to advertising expenditure, I introduced another variable, X2. And that variable is the number of years of education the person buying that car has. So equation 2 says, I want to try and see how much of sales of Tesla's electric cars, electric battery cars, whatever, can be explained by not only advertising expenditure, how much Tesla spends every advertising those cars, just like in equation 1. But in addition to that, I want to introduce all those, each person that buys Tesla's cars, how many years did they spend in educating themselves? Did they stop at high school? In that case, maybe they spent, high school is what, 12 years? Or did they go to college? 4 more years of that, that's 16 years. Or did they go to university? Did they go to college and then master's degree, 2 years, that's 6 years over and above high school? Or are they crazy enough to go for PhD, which is like, I don't know how long you spent for PhD, let's say average of 5 years. So that's 5. So why would we want to add years of education? Because our hypothesis is that the more educated you and I are, okay, and we can proxy our education by the number of years we spend in school, grade level, high school, university, master's, PhD. We can proxy our education by how many years we spend getting our degrees. That we believe the more educated you are, then the more you can appreciate electric battery cars, no pollution, blah, 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 all of that stuff. We could be wrong, but that's our hypothesis. So now we introduce the second variable and we run the regression and we have y equals maybe 4.3 plus 1.9 plus 3.2 x2. And then we see r squared is 85%. Whoa! And you guys will say, oh, Professor Anache, you're so good and so good. So are you telling me that I would prefer equation 2 to equation 1? Yes or no?
No, not
Who says
necessarily.
Who says no? Who says
Me.
Please don't tell me
Ah.
not. Please don't tell me not entirely, because that's politicians' answer. I want somebody to be very categorical. Yes or no? I'm sorry,
Yes.
that's unfair, but that's unfair of me to do because it always depends. But I want to hold you to yes or no. Does that mean anytime I want to work with sales, maybe predict sales of Tesla's cars, how many dollars of Tesla's cars are sold each month, I should use equation 2 over equation 1? Yes?
Yes. I say yes.
Okay, who says yes? And I want one person that says yes and any other person that dares to say no. And if you dare
Yes.
to say,
I said yes.
hey. And if you dare to say no and you are wrong, then the first glass of wine at Baruch College, you buy it for me and the rest of the class. All right. Who says yes?
Yes.
So
Professor.
yes. Wait, hold on. Let me ask the question and then I can take your question. So yes, meaning I should use equation 2 over equation 1 because r squared for equation 2 is better than equation 1. Categorically, I should use equation 2 instead of equation 1. Who says yes for equation 2? Come on, guys. You made A's. You passed Echo 4000.
I say yes, Professor.
Okay, who are you again? I don't see you.
I am Natalie.
Ah, Natalie. Okay, Natalie say yes. Okay. Who else says yes, supporting Natalie?
I think it's yes.
Roxolana. Oh, Roxolana, you've just said hello to your professor today. How are you?
Hi, I'm good. How are
Okay.
you?
So Roxolana says supports Natalie, and I'm sure many other people support Natalie. But is there a brave soul that says no?
Professor, we gotta
Professor.
look at something else. We can't just look at the r squared.
Who is talking? Alec.
Alec, we gotta look at the adjusted r squared to get an answer to
Alec,
your question.
how dare you contradict your professor? I mean, this guy is contradicting his professor. That means you must be wealthy. You are getting ready to buy wine for everybody in this class. Okay, go on, Alec, explain.
So by the introduction of another variable, regression, then what we
Alec,
can see
don't go fancy on me now. He's using
Okay.
regression.
Okay.
You're such a show off. but you're correct though. But by introducing another x, I'm introducing
Another
another
right.
regressand. You're correct. I'm just messing with you. Go ahead.
the r square automatically increases, but that doesn't mean that the model fits better the data set.
Excellent. So I'm buying the wine
Thank
for
you.
you. So if you catch me at Baruch, I'll buy the wine.
I buy you the first round and you buy the second round
Okay.
if I get an A for this
Okay.
class.
because all of you, Natalie and Roxolana, all of you that supported Natalie, you missed that point. I think you assume that when I said r squared, that I also meant adjusted r squared. So I kind of snuck in that trick, but Alec caught it. Because the truth is this: anytime you run a regression like equation 1, you use only one x variable and you get r squared of 80%. If I introduce another x, x2, and another x, x3, even if x2 and x3 really have nothing to do with Tesla's sales. For example, if I say x2 is, for example, in equation 2, I say x1, y is sales of Tesla cars, x1 is advertising expenditure, the same as equation 1, but x2 is the number of accidents in the most remote village in Russia. And then I introduce equation 3. X3 is the number of peanuts Joseph Onoche consumes in Azerbaijan. Things that have nothing to do with Tesla cars. It is possible that R squared will go up, just like we see in equation 2 and equation 3. So because of that, I'm sure you just forgot. This was explained to you in your statistics and Echo 4000 class. That's why we use adjusted R squared, because adjusted R squared does two things over R squared. Adjusted R squared says, okay, if I introduce x2 in addition to x1, if I introduce x2 like in equation 2, then the first part of R squared will tell me the explanatory power. But the second part will be a penalty, because I'm aware that the more x's I introduce to the right-hand side, the tendency is for R squared, ordinary R squared, to go up. But then adjusted R squared penalizes me for introducing additional variable which may not have explanatory power. And then if I do x2 and x3, then that R squared can go up, but adjusted R squared will, yes, introduce maybe additional explanatory power, but also penalize me for introducing two additional regressors, according to Alec, which is correct, two additional x variables that may not be explanatory adequately, but which just by introducing two of them will increase the ordinary R squared. That's why whenever you go from simple OLS, ordinary list regression, OLS, to multiple linear regression, you stop using R squared. You begin to use adjusted R squared, because adjusted R squared gives you the number for the explanatory power plus some penalty. And that penalty recognizes the fact it wants to remove the impact on ordinary R squared of us introducing additional x variables. You get it? So look, equation 1, 2, and 3, the R squared is 80%, 85, 90%. Based on only these three R squareds, you can say, oh, let's use equation 3. But if we add, if I show you adjusted R squared for equation 1 is the same as its R squared, 80%. But adjusted R squared for equation 2 may be 78%. And adjusted R squared for equation 3 could be 75%, in which case, actually, equation 1 is the best equation. Okay? Look, believe me, I'm a professor, so I deal with students every day. What you say and what you think, they are two different things. So many of you, I'm sure, when you saw R squared for equation 2 and 3, in your mind, you're thinking adjusted R squared. Because anytime you have more than one x, you don't use the R squared. You introduce adjusted R squared. If you have only one variable, x1, as in equation 1, the ordinary R squared is the same as the adjusted R squared. So we always just report the R squared. Okay, so R squared is typically what we use in OLS, in least squares regression analysis. It's typically what we use to test for how good the model is. By the model, we say how good the equation is. Okay, and if if we're using only only x1 only, we call it in the language, in the profession, we call it simple linear regression. Simple because we have only one x variable on the right-hand side. Then R squared is as good as adjusted R squared. But once you introduce two different variables on the right-hand side, then you don't use R squared anymore. You use adjusted R squared, because adjusted R squared tends to adjust to penalize us for the increase in R squared that will typically occur when we introduce an additional variable. Okay, guys? Okay. Any questions? All right. In time series analysis, in addition to the ACF and the PACF that we have done, typically what we want to achieve is, sometimes when you look at the ACF and the PACF, believe me, I have done this enough times over the years. When you begin to do it and you begin to do it, sometimes it's not even as clear cut as I was explaining before the midterm exam. If you guys notice, the last class before the midterm exam, I don't know if you remember, but I actually simulated an AR1 model, AR2 model, and AR3 model. And I said, let's look at the ACF and the PACF for the AR1 model. It was perfect. The ACF was exponential, and the PACF was at lag 1. The line broke through the confidence area. So that was perfect. But I don't know if you recall, for AR2 and AR3, we didn't achieve that. Even though, you were looking at me when I simulated the AR2 and the AR3. So I was sure that was the AR2 model. I was looking at the ACF and the PACF. If you guys remember, the PACF didn't tell us that the line in lag 1 and the line in lag 2 broke through the confidence level, because the one in lag 1 broke through, but the one in lag 2 didn't break through. And somewhere down the line, I think one of them almost broke through, even though I was sure that was an AR2. The same for an AR3. I started off with an AR3, but when I looked at the ACF and the PACF, it didn't tell me conclusively that those were AR2s and AR3s. So sometimes we are not very sure, even after looking at the ACF and the PACF, we are not very sure. Okay? Because it might tell us that it's an AR1 model, but then somewhere down the line, the PACF in lag 3 will break through. So we're not sure whether it's an AR1 or AR3. We're not sure whether it's an AR2 or AR5. We're not sure. Okay? So in time series analysis, in financial econometrics, we have one more tool to help us to make reasonably sure. And that tool is what we call information criterion. All right? Information, let me see if I can type it here. Okay, that tool is called information criterion. Okay, information criterion. And hold on, let me see if I can tell you where it is in your textbook, but you don't have to go to your textbook at all. I will explain that, and then sometime during the maybe next class or possibly next Tuesday, I'll do an R programming. I'll give you the commands for the R program. All right, this is on page 61 of your textbook. So please, pardon me, let me go to your textbook now. And just let me show you where it is, so that those of you that like reading the textbook, which should be all of you, you can go there and begin to just look at it. Page 61. All right. So this is on page 61 of your textbook. And look here, it says information criteria. Because I'm going to introduce you to two types of information criterions, but we don't call it criterions, we call it criteria, plural. There are two types. The first information criterion, we call it the akaike information criterion, the AIC. Okay, and the second one is the Bayesian or Schwartz. Let's go to page. Gosh, this Adobe drives me crazy sometimes. Okay, the second criterion is called the Bayesian information criterion, but or BIC. Okay, BIC. Look at it up here. Bayesian information criteria, but we also call it the Schwartz because maybe Professor Schwartz discovered it. And the first one, we call it the AIC, akaike, because I think the professor that discovered it, or the guy that discovered it, is Professor Akaike, Japanese, I think. Okay, so the information criteria, there are two, the AIC and the BIC. There are when I do my research work, I use 4 of them. Okay, but your textbook gives 2, so I'm going to stick to 2. So the AIC and the BIC, you can think of them in a kind of funny way. You can think of them as one way we use to settle the dispute. Maybe when we look at the ACF and we look at the PACF, we are not quite sure whether it's categorically an AR1 model, an AR2 model, or an AR3 model that we should use to represent Microsoft series. We look at the ACF, and the ACF tells us it's an AR model. But then when we look at the PACF, my God, we see the line in lag 1 shoots beyond the confidence interval. So we say, okay, it's an AR1 model. But then we look further down the line at different lags. We see those lines, they are kind of, just a little bit on the borderline of the, look, just like here. If you look at this diagram, this partial ACF here, luckily is here. Look, suppose I simulated this data series, and I know it's an AR, let's say it's an AR2 for sure. I know it's an AR2 model for sure. Okay, guys, can you see this, my cursor moving up here, the PACF? Somebody tell me yes or no. Okay, so suppose you and I, like I did before the midterm exam, suppose you and I actually simulate an AR2 model. And then we look at the ACF. Okay, it behaves very well. So we say, bingo, it's an AR model. But then we look at the PACF, and some funny thing like this diagram shows up. Look, this is the partial autocorrelation function, the PACF. And we see that, okay, it breaks through in lag 1, breaks through a little bit in lag 2. So, and you and I, we simulated an AR2. So we are sure it's an AR2. But then look, at 3, it breaks through. At 6, okay, it's just not making up its mind. And then at 9, it breaks through. So, my God, what's going on? Even though you and I definitely simulated an AR2 model. So instead of ripping out our hair that I don't have, we say, okay, fine. Let us apply the information criteria. So we say, look, okay, right, professor said, you observed me, I simulated an AR2. But this diagram is telling us it could be AR2, it could be AR3, and because this one is breaking through on the negative side, so the coefficient on the xt minus 3 is negative. this coefficient at xt minus 6 is not making its mind. So maybe let's include that. This coefficient, at lag 9 it broke through. So this could be an AR2 model. That's xt minus xt. The equation xt equals the constant plus xt minus 1 plus xt minus 2 minus xt minus 3 plus a little bit of xt minus 6 plus xt minus 9. We can throw all the x's at these lags in, and we say, okay, let us run 4 regressions. The first one is xt minus 2. So we say xt equals a constant plus a constant times xt minus 1 plus a constant times xt minus 2, because this tells us it looks like an xt minus 2 model. Then we say, let's run another model. Xt equals constant plus coefficient times xt minus 1, xt minus 2, and then we introduce xt minus 6. That's another equation. And then we run a fourth equation. Xt equals xt minus 1 plus xt minus 2 minus xt minus 3 plus xt minus 6 plus xt minus 9. So the third equation has all the lags where the PACF broke through the confidence bound. The second equation has only up to the lag 6. It doesn't have the one in lag 9. Then the first equation has only lags 1 and 2. So we estimate those equations, and then we look at their information criteria, either the AIC or the BIC. Okay? Generally, most people will look at the AIC for a reason I'll give you later. Now, if the AIC or the BIC so the AIC and the BIC equation, let's not use the BIC for now. Let's talk only about the AIC, the akaike information criterion. We're looking for the model that has the smallest AIC. Smallest, not the largest. When we did R squared in Echo 4000, we are looking for the equation that has, we are looking for the regression model that has the largest positive R squared or the largest positive adjusted R squared. But when we use this information criteria, either AIC or BIC, we are looking for the AIC number that is the smallest. If the AIC for all the equations, all the 3 equations I just mentioned, if the AIC for each one is positive, then we're looking for the AIC that is the smallest positive number. And that model is the best model, is the best equation to use. But if all the AICs are negative, then we're looking for the largest negative number for the AIC. The AIC that has the largest negative number would be the equation that is best out of all the possible equations we're estimating. Okay? Okay, so again, we're going to see that result.
Wait, sorry, Professor, can you repeat that? The largest negative number?
Yes.
Okay.
Okay, so for example, let me go back to Echo 4000. If I run 3 equations, and the first equation has adjusted R squared of 90%, the second one has adjusted R squared of 60%, the third one has adjusted R squared of 95%. Then obviously, everything else constant, the one with the adjusted R squared of 95% is best, yes?
Yes.
Yes, because R squared cannot take on a negative number. R squared typically will be positive. Okay. But for the information criteria, if we calculate information criteria, and by no means are you going to calculate it by hand, R will give them to us. If I run the AIC, if I look at the AIC for like 10 equations, for 10 autoregressive equations, and all the AICs are positive, then I will choose the AIC with the smallest positive number. Okay, Lily, Roxolana, who asked me that question?
Yeah, it was Roxolana. Okay, that makes sense.
Okay, but then unlike R squared, the information criteria can also take negative numbers. Okay, so if I have 10 autoregressive AR equations, AR1, AR2, AR3, and I run them all, and all of them, their AIC, each of their AICs is negative, then the best model is the one that has the largest negative AIC. You got it, Roxolana?
Yes, and I'm sorry if you mentioned this before, but for BIC,
it's the same, whatever I say for AIC is exactly the same way to choose with BIC, okay?
Okay, great, thank you.
But sometimes if I have 10 autoregressive models, AR1, AR2, AR3, AR4, AR15, and I run all 10, and I want to look at AIC and BIC, okay, for the same 10 equations, then AIC and BIC can give me contradictory conclusions. The one with the smallest AIC might not be the one with the smallest BIC. Okay, so we usually advise you choose one and stick to one. Okay. I mean, let me see. I think there's an example here. Let me just, please give me 1 second. Okay, let me go back to page 61. Okay, look at table 2. Look at table 2.1. You are staring at it immediately. So look at PACF. Okay, I have run the PACF for like 1, like 2, like 3, like 4, like 5, like 6, like 7, like 8, like 9, like 10, like 11, like 12. Can you guys tell me, using the AIC, for which lag is AIC smallest? From lag 1 to lag 12.
Lag 9.
Okay, so for lag 9, the AIC is smallest at 5.849, right? Because it's the largest negative. Is that correct?
Yes.
Okay, thank you. For the BIC, at which lag is the BIC smallest?
Lag 7.
Lag 7. How about lag 1?
Lag 1.
You see, lag 1 is negative 5.833, yes?
Oh, true. Yeah.
That's larger than lag 7. So if I use AIC and BIC, then AIC tells me this is an AR9 model. But BIC tells me this is an AR1 model. You see that? So it's contradictory. So we always recommend, if you want to use AIC, stick to AIC. If you want to use BIC, stick to BIC. Most people stick to AIC because AIC is less stringent. BIC applies typically a larger penalty than AIC. Okay? Now, let me scroll down. Where is this? This is page 62. Okay. So look, page 62, BIC has 2 portions. Look at this equation at the bottom of this page. BIC at any lag, is equal to natural log of this thing plus this thing. Okay, this first portion is the actual explanatory power. But this second part is the penalty we put, because the more lags you add, the more you tend to have increasing explanatory power. So we penalize it. So that is why it is like the same idea as adjusted R squared and R squared. Adjusted R squared adds a second term, and that second term is a penalty. Okay? And if you look at AIC, this, which is the final thing I'm going to discuss tonight. Okay, look at AIC. AIC has two components. The first component is exactly the same as for the BIC, but the second component, the equation, is different for AIC than for BIC. And generally, they say the AIC is applies less penalty. It's more relaxed than the BIC. So many people tend to use AIC because it's more, it's more relaxed than the BIC. Okay, so I'm going to stop here. And on Thursday, I will introduce another new concept. Again, I won't use equations. I won't use R. I'll just introduce that concept. So after Thursday, the next Tuesday, I can go to R and illustrate with the commands of what I've explained today and what I will explain on Thursday. Okay. All right. Thank you, everybody. Thank you for your attention. I'm going to stop recording now.
The recording has stopped.
Okay. So today we focused on information criteria. We looked at two, AIC and BIC. All right. Sometime in the month of, if you're interested, I will introduce other information criteria just for your interest outside of class. Okay. But for this class, we're looking at two of the information criteria: the akaike AIC and the Schwartz, the BIC, the Bayesian. Okay. All right. I'll see everybody on Thursday, okay? Everybody? Au revoir. Très bien.
Thank you.
Bye-bye.
Good night.
Professor, what chapter are we on?
We're in chapter 2. What I explained today is on page 61. I showed it to you in class. Page 61 and 62, okay? Of the textbook. You can go look at it. Don't worry about the equations, but just go look at it. Hey, Ian, thank you. How are you doing, Ian? All right. See you, Danny. See you, Alec. Thank you, guys. See you, Andrew. You didn't talk to me today. That's okay. William, I'll see you.
Professor, by penalty, do you mean, is that similar to like the residual? Like when looking at the equation?
It's not like residual. Just think of it as, because if you, for OLS, if you add more, see you, Mer Sylvie, for OLS, if you add more variables, the ordinary R squared will go up. So what I mean by penalty is that we will recognize that fact and subtract from the ordinary R squared. We'll subtract the tendency for the ordinary R squared to go up. We shall adjust that tendency. That's what I mean by penalty. But we'll call it adjusted R squared after we've done the penalty. That's what I mean. Okay.